Welcome to Everyday Mathematics. Today we begin a new series. This series is going to be on what we would call almost impossible integrals, sums, and series. And this is based on the book titled this same title here. The first problem in that book is the indefinite integral, rather the definite integral from x equals to 0 to x equals to 1 of 1 over 1 plus yx over times square root of 1 minus x squared. And this is in the interval of y between -1 and +1. We're going to see that this problem will lead us to actually show why the summation of 1 over k squared from k equals to 1 to infinity is actually equal to pi squared over 6. And this is what is called the Basel problem. So this integral will help us solve the Basel problem, help us link that infinite summation to a constant pi squared over 6. So very interesting. Without much ado, we'll move forward to that solution. And before we actually even move to that solution section, I'd like to encourage those of us who haven't subscribed to our channel, please, if you can, stop the video and subscribe to our channel. Your support will go a long way in just giving us that extra profile that we need. If you like the video, please leave a like. If you think somebody else might benefit from this video, please don't hesitate to share. So let's move on to the solution section of this video. Is this definite integral from x equals to 0 to 1 over 1 over 1 plus yx times the square root of 1 minus x squared, right? As first of all, this is in this interval of interest, y between -1 and +1. So when faced with such a problem where you have a square root of 1 minus x squared in the denominator, we begin by substituting and saying let x be equal to sine theta. And what that means is that dx d theta would be equal to cosine of theta, such that dx is equals to cosine theta d theta. So that's important. Now in the interval x between 0 and 1, we would see that when x equals to 0, what that means is that sine theta equals to 0, implying that theta is equals to 0. When x equals to 1 means sine theta is equal to 1, implying that theta is equals to pi over 2. Therefore, in the theta domain, our problem, which is becomes integral from theta equals to 0 to theta equals to pi over 2 of 1 over 1 plus, we said x is equals to sine theta, so we have y sine theta, square root of 1 minus sine squared theta, and dx we saw here is cosine theta d theta. So in this interval here, this guy here is safely cosine theta, so we have 0, pi over 2, 1 over 1 y sine theta, cosine theta over cosine theta, such that our problem now just becomes integral from theta equals to 0 to theta equals to pi over 2 of 1 over y sine theta. So we've gotten to this point here. Now proceeding forward, we have to make a certain modification. So let's say 0 to pi over 2, 1 over 1 plus y sine theta. There. So we can move from the single angle formulation to a half angle formulation. But it's important to know that sine squared theta over 2 plus cosine squared theta over 2 is equals to 1. So this is an important identity that we're going to use. And it's going to go there. So we have our problem now become integral from theta equals to 0 to theta equals to pi over 2 of 1 over sine squared theta over 2 plus cosine squared theta over 2, and this is in place of this, plus another identity, sine theta is equals to twice sine theta over 2 cosine theta over 2. So using that identity, we'll have 2y sine theta over 2 cosine theta over 2, right? So let's divide both the numerator and the denominator by cosine squared theta. So we have 1 divided by cosine squared theta over 2. And then here, divided by cosine squared theta over 3, right? So this becomes 0 theta over 2. The numerator becomes sec squared theta over 2. And here we would have tangent squared theta over 2. Here would you have 1 plus 2y tangent theta over 2. So that's where our problem has brought us. After that, it's easy to see that sec squared theta over 2 is something akin to the derivative of tangent theta over 2. So if our problem is that, if we say let u be equal to tangent theta over 2, then that means that du d theta is equals to a half sec squared theta over 2, implying that 2 du is equals to sec theta over 2 d theta. So this is an important substitution. So when theta equals to 0, tan theta over 2 is equals to 0, meaning that theta is equals to 0. When theta is equals to pi over 2, that means, this is u. We see that u is equals, and this is 0, u is equals to tan pi over 4, such that u, and this is also u, u is equals to 1. So let me just rewrite that so that there is no ambiguity. So let's delete this, delete that. So z is equals to u and u is equals to 0. Okay, so our problem here now becomes if we have 0 pi over 2 plus 1 plus 2y tan theta, this is the same as 0 to 1 to du, and this is u squared plus 1 plus 2yu. In place of tan theta over 2 we have u. In place of sec squared theta d theta, sec squared theta over 2 d theta, we have 2 du. So our problem now is 0, 1. We have 2 out here, and we have du over u squared plus 1 plus 2yu, which we could rewrite as u plus y squared plus 1 minus y squared. So this comes from u plus y squared is equals to u squared plus 2yu plus y squared, such that this and that, u squared plus 2yu is equals to u plus y squared minus y squared, taking this side. Okay? And another way we could express this is plus square root of 1 minus y squared, right? Such that when we now go ahead and say, if we to substitute for this, say let t be equal to u plus y, that means that dt du is equals to 1, meaning that dt is equals to du. And so when u is equals to 0, t is equals to 0 plus y, which is equals to y. When u is equals to 1, t is equals to 1 plus y. So our problem becomes twice from integral from t equals to y to t is equals to y plus 1 of 1 over t squared plus the square of the square root of 1 minus y squared. Okay, so that's actually progress. So our problem is now integral from t equals to y to t equals to 1 plus y of 1 over t squared plus the square of the square root of 1 minus y squared. Which is important because now we can say let, because it's an easy problem here, an arctangent problem. So we say let t be equal to, there's a square here, square root of 1 minus y squared tangent of phi, such that dt d phi is equals to square root of 1 minus y squared sec squared phi. And so dt now can be expressed as 1 minus square root of 1 minus y squared sec squared phi d phi in the phi domain. And so when t equals to y, that means that y equals to square root of 1 minus y squared tan phi, and so phi is equals to the arctangent of y over square root of 1 minus y squared. And when t equals to 1 plus y, clearly we can see that phi is equals to the arctangent of 1 plus y over square root of 1 minus y squared. Okay, so what does that mean? That means that our problem that is twice the integral from t equals to y to t equals to y 1 plus y of 1 over t squared plus the square of 1 minus y squared is equals to twice the arctangent, integral from arctangent of y over square root of 1 minus y squared to the arctangent of 1 plus y over square root of 1 minus y squared of dt happens to be the square root. Let me delete that. The square root of 1 minus y squared sec squared phi over t squared would be 1 minus y squared square root squared tan squared phi plus the square of the square root of 1 minus y squared, right? And we have d phi here. So we can pull this out and also this out so that we have 2 square root of 1 minus y squared over the square of the square root of 1 minus y squared. So this and that would cancel. Integral of sec phi over 1 plus tan square phi would also be sec square phi. So this becomes twice or 1 over square root of y squared integral of 1, which is 2 and sorry, we have limit here, y over square root of 1 minus y squared arctangent square root of 1 plus y over square root of 1 minus y squared. So here we do have the same thing, arctangent y over square root of 1 minus y squared, arctangent of 1 plus y over square root of 1 minus y squared. So we have phi arctangent y minus square root of 1 minus y squared, arctangent of 1 plus y over square root of 1 minus y squared. Okay, so this leads us to, so since we have this expression, this becomes 2 square root of 1 minus y squared arctangent of 1 plus y over 1 square root of 1 minus y squared minus the arctangent of y over. Okay, we certainly could make this a little more simpler than it is right now here by saying if u, or let's just say, yeah, if u be equal to, let's involve this guy as well, twice the the arctangent of 1 plus y over square root of 1 minus y squared minus the arctangent of y over square root of 1 minus y squared. Then u over 2, and we say tangent of that is equals to tangent of the arctangent of 1 plus y over square root of 1 minus y squared minus the arctangent of y over square root of 1 minus y squared. Okay, you have a tangent of a minus b, right? That's the same as tangent of a minus tangent of b over 1 plus tangent of a tangent of b. So since tangent of u over 2 is equal to tangent of arctangent 1 plus y over square root of 1 minus y squared minus arctangent of y over square root of 1 minus y squared. This means this is the same as tangent of the arctangent of 1 plus y over square root of 1 minus y squared minus tangent of arctangent of y over square root of 1 minus y squared over 1 plus tangent arctangent of 1 plus y over square root of 1 minus y squared tangent arctangent of y over square root of 1 minus y squared. So this becomes tangent of arctangent, we just get 1 plus y over square root of 1 minus y squared minus tangent of arctangent, we have y over square root of 1 minus y squared over 1 plus y over square root of 1 minus y squared times y over square root of 1 minus y squared. So since our tangent of u over 2 is equal to 1 plus y over square root of 1 minus y squared minus y over square root of 1 minus y squared over 1 plus y over square root of 1 minus y squared times y over square root of 1 minus y squared. We can see quickly that here the denominator is common here, so we have 1 plus y minus y, this cancel, square root of 1 minus y squared over this multiplied together, and so we have 1 minus y squared plus this times this is y, this times this is y squared over 1 minus y squared, this times this. So this cancel, and what we see, since we have 1 here, this becomes square root of 1 minus y squared over only this plus this, so 1 plus y. Okay, and since 1 minus y squared is the same as 1 plus y, 1 minus y, it means that the tangent of u over 2 is the same as square root, a big square root of 1 minus y, sorry, over 1 plus y, bracket. So we've come to a point where tangent of u over 2 is the square root of 1 minus y over 1 plus y. And so if we have a triangle here, and the base angle is u over 2, it means the tangent being opposite over adjacent means the opposite will be 1 minus y. The adjacent would be square root of 1 plus y. And so the hypotenuse is going to be square root of opposite plus, and so this cancel, which is equal to square root of 2. So what does that mean? It means that cosine of u over 2 is equals to square root of 1 over 2. Sine of u over 2 is equals to square root of over 2. And if we want to represent this as a cosine formulation, so cosine of u is the same as cosine, could even just say twice cosine squared u over 2 minus 1, which is 2 square root of 1 plus y over 2 squared minus 1, which is 2, 1 plus y over 2 minus 1, which is y. Therefore, u is equals to arc cosine of y. Important relationship. And since we had shown from our previous integral that our integral of from 0 to 1 of 1 over 1 plus yx square root of 1 minus x squared was equal to twice from y to 1 plus y 1 over t squared plus the square root of 1 minus y squared, which we show to be twice square root of 1 minus y squared arctangent of y plus 1 over square root of 1 minus y squared minus the arctangent of y over that u, which is equals to twice the arctangent of y plus 1 over square root of 1 minus y squared minus the arctangent of y over square root of 1 minus y squared. This means that this is the same as, so this part here is equals to arc cosine of y, right? With that in mind, it means that our problem here is equals to arc cosine of y over the square root of 1 minus y squared. So this is important, and this is for the interval y between -1 and +1. What if we said, okay, we want to integrate that problem, right? In that y domain. We want to integrate that. That would be arc cosine of y over square root of 1 minus y squared sorry, this is dy. This is going to be a problem. And I would say let u be equal to arc cosine of y, such that cosine of u is equals to y, and so negative sine of u du dy is equals to 1, meaning that negative sine of u du can be used to substitute for dy. And what does that mean? That means that when y equals to -1, we have sine of u being equal to -1, and so u would be equal to pi. When y is equals to +1, cosine of u would be equal to 1, and so u would be equal to 0. So therefore, -1 to 1 of arc cosine of y over square root of y squared would be equal to pi 0 cosine, this is u over square root of 1 minus cosine squared u, and this is dy is negative sine u du. So this becomes negative pi to 0 of u. In this interval here we have sine u du, and this becomes negative from pi to 0 mu to u, which is negative u squared over 2 from pi to 0, which is equals to pi squared over 2. There. So what that really means for us is that this big integral from y is equals to -1 to y equals to +1 of the integral from x equals to 0 to x equals to 1 of 1 over 1 plus yx square root of 1 minus x squared is equals to pi squared over 2. So this takes us to a situation where if we have a continuous, let's say this is z, right? And then we have the x, right? And then we have the y. Okay. And we do have contours. Let's say something like that. That, and right, and then along the y direction, I mean something like that. We have something like that. So if we decided to integrate, we could integrate along the x first, or along the y. So we could do something like that, integrate along the y, and then later integrate that panel in the x direction. Or we could as well just integrate in this direction and then integrate in the y direction, or the other way around. So what I'm trying to say here is that you could flip the order of the integration and still be okay. So what does that mean? It means that if we have this integral, this is the same as 0, 1, the same thing, right? And so let's try to focus on that. I can pull this guy out here because there is nothing in the y direction involved there. So I'll have 0, 1, 1 over square root of, and then I have it's so here what we see is we have 0 to 1, log of 1 yx over x, negative 1 positive 1 dx, which is the same as 1 over, and pull that x out, and we have log of, substitute 1 plus x minus log of 1 minus x. So this becomes integral from 0 to 1, the square root of 1 minus x squared, and we have 1 over x log of 1 plus x minus log of 1 minus x. And we can actually use the rules of logarithm there to say that we have 0 to 1. Let's pull this here. So we have 1 over x square root of 1 minus x squared times the log of 1 x over 1 minus x. Okay, so this is becoming tractable. We can reverse the order of this so that we pull the negative out. So we have negative times the negative 1 times the integral from x equals to 0 to 1 of 1 over x square root of 1 minus x squared, natural logarithm of 1 minus x over 1 plus x dx. I think the next thing is to try and substitute for that, and we'll say let u squared be equal to 1x over 1 plus x, which is same as 2, 1 plus x, 2 minus 1 plus x over 1 plus x, which is 2 over 1 plus x minus 1. Let's just focus. We have u squared being equal to 2 over 1 plus x minus 1. When we differentiate both sides with respect to x, we have 2u du dx being equal to negative 2, 1 plus x squared. And obviously these two can cancel, so essentially what we find is that u du can be used to substitute for negative dx over 1 plus x squared. Right? And our original problem, negative from 0 to 1, integral of 1 over x square root of 1 minus x squared times natural logarithm of 1 minus x over 1 plus x can be rearranged. And we want to express this dx in this format here as follows. So we have 0 to 1, 1 over x over 1 plus x, square root of 1 minus x squared over 1 plus x, and this negative here can be brought. So let's first of all write natural logarithm of 1 minus x over 1 plus x, negative dx over 1 plus x squared. We wrote this twice so that it can cancel away with that. This is just for us to be able to see how to substitute things. Since 1 minus x squared is the same as 1 plus x times 1 minus x, this expression can change as follows: 1 over x over 1 plus x, square root of 1 minus x over 1 plus x, natural logarithm of 1 minus x over plus x, negative dx 1 plus x. This is squared. So what is this? What is this? Since u squared is equals to 2 over 1 plus x minus 1, 1 minus u squared is the same as 1 minus minus, so this becomes 2 minus 2 over, which is equals to 2 plus 2x minus 2 over 1 plus x. So this cancel. So what that means is that 1 minus u squared is equals to 2x over 1 plus x, implying that 1 minus u squared over 2 is equals to x over 1 plus x. This guy here is equals to this. So our problem, which is 0 to 1, 1 over x plus 1 or 1 plus x, square root of 1 minus x over 1 plus x, log of 1 minus x over 1 plus x, so since u squared is equals to 1 minus x, u du is equals to negative dx over 1 plus x squared, and 1 minus u squared over 2 is equals to x over 1 plus x. Using this relationship, this problem of ours becomes now, and obviously when x equals to 0, u squared is equals to 2 over 1 minus 1, which is equals to 1. Therefore, u is equals to 1. When x equals to 1, u squared is equals to 2 over 2 minus 1, which is equals to 0. So u is equals to 0. So our problem becomes from x equals to 1 to 0 of 1 over, this part here becomes 1 minus u squared over 2. This part here becomes u squared square root, which is u. This part here becomes log of u, and this part here becomes u du. So this and that cancel, and this is u squared rather. So we have 1 to 0 log of u squared over 1 minus u squared over 2, right? And this becomes 4, 1, 0. This 2 goes out here, and this climbs up here to make 4. So log u over 1 minus u squared. Okay, so we've made progress. We've made progress. Now, the next thing for us is to reverse the. So we have negative 4, 0, 1, the limits. So we have natural log of u, 1 minus u squared. This is important. This is important. So if our problem is that this part here where there is a hidden one at the top is important for us. And why is it important? Because when we have a geometrical progression with x less than 1 from k is equals to 0 to infinity, this becomes 1 plus x squared plus x3 all the way to infinity. Now, what about if yeah. So if we multiply by x, in other words, k is equals to 0, infinity, and x k plus 1, this becomes x plus x squared plus x to infinity. So what about if we subtract? Yeah, if we subtract 2 from 1, in other words, 1 minus x is equals to 1 xk, meaning that our summation from k equals to 0 to infinity of x to the k is equals to 1 over 1 minus x. So this is an important, and yeah, we're just spending so much time here, but this is supposed to be an obvious expression. Anyway, so what that means for us is that, let's see, we have negative 4, 0, 1 log of u over 1 minus u squared. This is the same as so since we had k equals to 0 to infinity, xk being equal to, and this is the same as beginning from 1 to infinity of xk minus 1, which is 1 over 1 minus x. So we're going to use that so that our problem here is equal to negative 401 log of u, this part here, same as summation of from k equals to 1 to infinity of u squared k minus 1 using this part here du. And we can swap, integrating a sum of things is the same as summing the integration of individual parts. So we can bring this out. So integral from 0 to 1 of u, multiply this, we have 2k minus 2 natural logarithm of u du. This is cool because we have negative 4 summation from k equals to 1 to infinity 0 to 1 of u to the power 2k minus 2 natural logarithm of u. And so this is the same as 0 to 1 log of u times the derivative with respect to u of u to the power 2k minus 1 over 2k minus 1 du. Using integration by parts, where if you have a product of v and derivative of u and you integrate that, we have uv minus u times the derivative of v. Using that, and this being our u and this being our v, we do have now negative 4 summation of k is equals to 1 infinity initial uv becomes u 2k minus 1 over 2k minus 1 times log of u from 0 to 1 minus from 0 to 1 1 over 2k minus 1, we're pulling this constant out, and so we have u 2k minus 1 times the derivative of log u is going to be 1 over u. Okay, so our problem has gotten us to this summation where we have u 2k minus 1 over 2k minus 1 log of u from 0 to 1 minus 1 over 2k minus 1 integral from 0 to 1 of u 2k minus 1 times the derivative of log u, which is 1 over u. So this is easy. Limit as u tends to 1 of u 2k minus 1 over 2k minus 1 log of u minus limit as u tends to 0 of 2u 2k minus 1 over 2k minus 1 log of u minus 1 over 2k minus 1. This part here becomes u to the power 2k minus 2. So as you can see, as u tends to 1, log u tends to 0. So this entire part goes to 0. And this tends to 0. U here tends to 0. So this part tends to 0. So, and then this negative and this negative interact, so we do have 4 summation of 2k infinity of 1 over 2k minus 1, 0, 1, u 2k minus 2. Since our problem is it's gotten us to this, u 2k minus 2, this becomes 4 to 1 infinity 1 over 2k minus 1, and then here we have u 2k minus 1 over 2k minus 1, 0 to 1. Clearly we can see u is 1 at the upper limit, u is 0 at the lower limit, so we have 4 equals to 1 infinity 1 over 2k minus 1 squared. So in other words, our problem, since we inverted the integral from 0 to 1 of negative 1 to 1 of 1 over 1 plus yx square root of 1 minus x squared is equals to 4 times the summation from k equals to 1 to infinity of 1 over the square of 2k minus 1. But we had also seen that it's equal to pi squared over 2. Since these two integrals are the same, what that means is that this summation is equals to pi squared over 2, meaning that summation from k equals to 1 to infinity of 1 over 2k minus 1 squared is equals to pi squared over 8. So this is the first step. So since we've found that the summation from k equals to 1 to infinity of 1 over 2k minus 1 squared is equals to pi squared over 8. We also know that when you're summing from 1 to infinity of 1 over k squared, this is the same as the even parts plus the odd parts, right? And with this part, this is very easy because 2 squared is 4, so we have a quarter. And we already know what that is, and this is the same as this. This and this are the same. So in other words, we have 3/4, because we're subtracting this both sides, from k equals to 1 to infinity 1 over k squared is equals to that. Okay. 3/4, the summation from k equals to 1 to infinity of 1 over k squared is equals to the summation from k equals to 1 to infinity of 1 over 2k minus 1 squared. But this already is pi squared over 8. So in other words, 3/4 summation from k equals to 1 to infinity of 1 over k squared is equals to pi squared over 8, implying that summation from k equals to 1 to infinity of 1 over k squared is equals to pi squared over 8 times 4 over 3 by 4(2) by 4(1), which is equals to pi squared over 6. Therefore, the summation from k equals to 1 to infinity of 1 over k squared is equals to pi squared over 6. And this, ladies and gentlemen, is the Bezier problem. So that allows us to see how we can show or solve for the Bezier problem. So without much ado, that actually brings us to the end of our video today. I'd like to encourage you, if you haven't subscribed to our channel, to please subscribe to our channel. If you do like what you see, please leave a like. If you think somebody else might benefit from this video, please encourage them to, or please share with them. Until next time, bye bye.